I wanted to talk today about basically the evolution of a data stack. And what we see a lot from customers, having hosted a huge number of databases, is times when the application evolves to sort of outgrow what they started to do and what they sort of expected the problems they had to be. And Darwin helps here. Basically, databases like life yield to the people who evolved the best. And in particular, what we've seen is people start with the general purpose database, like Rethink, which is good for most of the data problems you'll have with a new application, good for some specialized data problems kind of at the level you'll probably have them, and not so good for really serious problems you might run into down the road. And we've seen a couple of cases of this. So the takeaway here is start with the simple thing and recognize when things get hard. And I'm going to give you some ways to do that and some things to look out for. What you'll typically find in a lot of databases is you end up, if you squint hard enough, you have what's called a graph problem, which is the Facebook problem, where you really want to think about relationships more than just rows. And you actually want to query over the relationships. And the canonical example of this is the 6 degrees of Kevin Bacon problem, where it's what's the shortest path from one actor to Kevin Bacon. It's by far the best real-world example of this is the only good picture I have for a data problem, so I started with that one. And you'll notice this when you're in a general-purpose database because you'll be doing things like an infinitely recursive number of joins to try and solve a problem. You'll see really complicated app logic weaved in with lots of queries. And it actually can work pretty well, but it's a bit limiting. And we saw this a lot with Mongo, particularly because Mongo became popular about the same time everyone wanted to hire a PHP developer to rebuild Facebook. And the first thing the PHP developer who wants to rebuild Facebook does is tries to do all these relationships in Mongo and then try and recommend friends based on who their friends are. And it works fine for 10 megs of data. This one actually doesn't work fine at all for even a few gigs of data. It falls over very quickly. There's a train with sound effects. And so this is the one we see a lot that people don't tend to recognize. Like I said, I think if you squint hard enough, you can find a graph problem in any database. And it's by far the least understood, I think, of data problems that people accidentally happen into. Oops, wait, I went down on this one. All right. We also see people that have kind of a flexible search problem. And this is an archaeological dig. And what happens in an archaeological dig is the archaeologists, they know roughly what the layout of a place they're looking at is, but they don't have a specific pointer to the thing they're looking for. They end up having to do a lot of creative stuff. They have to kind of be structured the way they think, not so much structured the way the data is organized. And this is roughly what we call a search problem. And something like Elasticsearch or Solr or even just Lucene if you want to implement this yourself. And the times we see this happening, or the times we see this create pain for people, is when they don't know ahead of time how their data is going to be queried. So general purpose databases, Postgres, Rethink, Mongo, are really, really good at fast queries if you know the queries ahead of time and you can actually optimize those and build indexes in a way that supports that use case. But they're not so good for letting users define queries, for instance. We have a customer that does marketing automation stuff, and their customers actually want to go in and say, give me a list of all of my users who have these attributes who are, between 15 and 40 years old, who visited on these dates, who are using this browser, and have paid me money, basically. And the more complicated that gets, the less well it works in, I think, the general purpose things. And so what the search problem becomes is you put your data in and you kind of describe the indexes more than you describe the data itself. So where you'll have either implicitly or in a strict schema, say this is a number, what you tell a search database is like, maybe this is a number and it'll be between these ranges. One of the things that you find in a lot of databases is GeoSearch. And Slava mentioned this the other day, but for most people's purposes, GeoSearch in the general purpose database gets you about 90% of the way there. But something like Elasticsearch is actually better at geo. It's not quite as good as like an actual geo database would be for something like mapping, but it's a little bit more expressive in what you can query. Other things are, you can do well, we've seen people try and do this too, where they actually tokenize blog posts, for instance. They'll have a few paragraphs of text. They'll split it into words. They'll try and store each word as a row or document in their database, and then they'll try and use that to do, full text search. And some databases have full text search built in. Again, it's good for getting you 80% of the way there, but it's really not that great of full text. It's more about a way to do it without kind of complexifying your infrastructure. Then we have time series data. And one of the things that I've found myself wanting to do in the past, and I think probably everybody runs into, is I'm going to store a number. And it's going to be, today I had 4,000 visits to my website. And storing that in a database is super easy. But then the question becomes, so what happened yesterday? What happened 3 years ago? And you can do this. You actually can redo your schema to give you some of this time series information so you can look at numbers over time, but it greatly complexifies things. And to do really good time series data, you kind of have to pluck that out and say, all right, I'm going to treat this a little bit differently than everything else I do. Because being able to instantly see exactly how many visits you got to a thing that particular day is simple, and it should stay simple. Plugging that stuff out and seeing it over time, doing some regression stuff on it, seeing what deviations and all these things should also be simple. You just can't quite do them all in the same database. If anyone's ever used Graphite, it was kind of the first time series database by accident. There are better options now. Some of them are built on Cassandra, which I'm not sure is always a better option, but you can do it. There's a database called Influx. It's very new that gives you kind of a SQL-y-like queryability over time series stuff. And then the last one is big data, which is kind of a joke in the sense that people think they have big data and they don't. When we talk about big data, what we talk about really is being able to ingest a lot of data and having to do a lot of analysis on it to make it mean something. And what we see a lot is people, particularly with Twitter feeds, the best way in the world to spend a huge amount of money on a database and not do anything useful is just try and store all the tweets that come through for a certain amount of time. And people do this, and it's odd because when you build an app in a general purpose database, you can make it fast. It's a small amount of data. It's really easy. It's good for users. But then they try and cram all these tweets in there too. And what ends up happening is they flatten their database. They ruin the experience for everybody in search of this sort of big data that's going to be super valuable someday if they can just figure out how. So this is actually the best picture because, honestly, this is exactly what putting your face in a Twitter feed feels like to people, especially when they get billed for it later. So one of the things to do when you're building an app is to kind of recognize the types of data problems you're going to have. Most of these things are rooted in math theory. Actually, a lot of relational databases themselves are just the implementation of some math. Things like graph databases are graph theory. Things like the time series databases are, I don't actually know the name of it, theory, but same general deal. So a lot of this is you just think about it. It's not really a thing you do. You just think about it because the same way you think about scaling. When you think, hey, I'm going to need to scale this to billions of users down the road, you don't build it for billions of users down the road. You make sure you're aware of the ways it's going to fall over and the ways to get yourself out of that situation. So think about it, but maybe don't do anything yet. Just kind of be aware. Be aware that I have a time series problem. Be aware that I might have a graph problem for two reasons. One, when it happens, you know what's happening. And two is just recognizing you have a graph problem, for instance, gives you a lot more intelligence about the types of things you can do for users. For instance, if you have any kind of many-to-many relationship in your database, which everybody does, you might actually be able to do stuff with a graph database to learn things about that, to give your users better experiences. So premature optimization is the root of all evil, even for databases. You should not start with Cassandra if what you need is CRUD. And you should not start with a time series database if you're just storing comment counts on a blog. So here's when you should use a specialized database. When it simplifies logic, a lot of this is development time. If you can save development time in exchange for a little bit of operational complexity, you're gonna have a better life. And this is the graph problem, for instance. You can do a lot of graph stuff with a not graph database, but it makes things really complicated. Making things fast. If you have your CRUD database, keeping it small makes it fast. If you can pull the other stuff you're doing out and treat it differently, you can keep a lot of your components fast and not have to make those kind of trade-offs for no good reason. And then to scale intelligently. Excuse me. The Twitter thing is a really good example, for instance. You need to process terabytes of information a day to handle Twitter feeds, which is a different class of problem than everything else you're doing. So if you can pull the problems apart, you can scale this one without having to spend a huge amount of money on your other problems, basically. that's it. And we host a lot of these databases. That's the other part of this.